So onward. Does anybody know what makes a joke into a dad joke? Good guess. A joke becomes a dad joke when it becomes apparent.
That's such a dad joke.
Exactly. All right. So orbital motion. Go ahead and label your notes orbital motion. We're going to talk about this for a little bit. Now, if we want to talk about orbital motion, we got to know what orbit is before we start getting into numbers and stuff. So, you don't have to draw this picture here, but feel free to just listen. So this here is Earth. There's Florida. We've got the UK over there, and Ireland. And there's Spain, and there's Australia. So this is Earth. And in order to understand what's going on with orbit, you have to know what happens if you go all the way up to the top of the Earth here. So this is you. And what you want to do is you want to take a baseball and you want to throw it as hard and as far as possible. So that's exactly what you do. You go up there, you throw that ball, and it lands right about there. Not super impressive. But you want to throw it even further next year. So you go back to the North Pole, and you let loose. After probably lifting some weights, you find that you've thrown the ball much further this time. And now you're like, wow, I can really improve on this. So now, maybe you enlist in Mr. Amano's speed and strength program, and you go back there and you throw it even harder. And now it goes all the way to Spain. And at this point, you're like, man, if I can do that, now I want to actually throw this ball all the way around the world so I get it right back. So, maybe after taking some special weightlifting supplements that are legal, you lift your weights again, you enroll in 2 of Mr. Amano's Speed and Strength programs, and you go back to the North Pole, and you just throw that ball as fast and as hard as you possibly can. And sure enough, it goes all the way around the world and comes right back to you. And this is what orbit is. You see, a lot of times when people think of objects that are in orbit around the Earth, and they see people who are on space shuttles and on the International Space Station, it appears they have no weight, like there's no gravity. But there is gravity. Even this ball that you threw all the way around the world is feeling the effects of gravity. It's falling. But the thing is, it's traveling fast enough that it's moving and going around Earth's curvature, instead of actually impacting the Earth. And that's what orbit is all about. It's about objects traveling fast enough that they fall around the object's curvature instead of actually falling into it. And that's what's happening here. It does not stay in this orbit because there's no gravity. It stays in that orbit because it's moving fast enough to constantly be in free fall. And that's exactly what orbit is. It's something that's constantly falling around the Earth. That's what's going on with the space shuttles. That's what's going on with the International Space Station. That's what's going on with satellites that are in orbit around the world. Now, you're going to feel weightless if you're on those things, because as we've talked about many times before, everything falls at the exact same rate without air resistance. Whether it's a feather or a bowling ball or anything else. Everything falls at 9.8 meters per second squared. If you go to Great America and you go on the giant drop and you bring something like a whiteboard marker with you, if you let it go at the instant that it drops, it's going to hover right in front of your face because everything falls at that exact same rate. And so when you're in orbit, everything appears to be weightless because it's all falling at that rate. Okay. Questions on that? Cool. So we're going to put some numbers with this, and then I'll show you the orbital model that I have in the back there. So hopefully this looks familiar. Force of gravity. That's equal to mg, and that's just fine. As long as you're on Earth's surface. If you change your distance from the middle of the Earth, if you go further off the surface of the Earth than where we are right now, this g value is going to change. What do you think? Is it going to get bigger or smaller? It's going to get smaller. The further away you get from the Earth, the less its gravity is going to affect you. So the thing is, if we're dealing with physics of objects that are in orbit, we cannot use that equation anymore because it is based on an assumption that you're on the Earth's surface. If you're not on the Earth's surface, that estimation of g being equal to 9.8 does not work anymore. And the further away you get, the more inaccurate your answers would be. So what we need is we need a new definition and a new equation for force of gravity. So I'm going to show you what that is. There's your new equation for force of gravity. So each of these letters means something different. The G is a gravitational constant. It is 6.673 times 10 to the negative 11th with a whole bunch of weird units after it that you don't need to worry about. But that's what the value G is going to be whenever you see it. M, the big M, is simply your big mass. This is the object that this is the thing that the objects are orbiting around. Usually it's a star or it's a planet, something like that. Little m is the little mass. So this is the satellite or the space shuttle or whatever it is that's actually doing the orbiting. Now this R here is arguably the most important of these because it's the most tricky. R is the distance from the middle of the big mass to wherever the object is orbiting. We'll just say distance to the orbiter, whatever's doing the orbiting. More specifically, this R, this radius, is the distance from the middle of the big mass to wherever that object is orbiting around. So that's what all these letters mean, and we'll just go through an example or two here. Let's just assume, for the next example's sake, that we are on Earth. I'm just going to get rid of these. So if we're talking about the force of gravity on the Earth, I'm going to label that with capital E. And the way I would just write that would be G M over R. But notice I, of course, put the E next to the mass for the mass of the Earth. And this R would be for the radius of the Earth. You want to make sure you're being specific about that. so that you don't forget which of those is which. And these numbers will be listed for you. They actually might even be on your formula sheet. I don't remember. I'll have to look. So yeah, that's how I would write that if I am doing this for Earth. Now, on Earth, the mass is 5.98 times 10 to the, I think it's 24th. Yeah. Kilograms. The radius of the Earth is 6.37 times 10 to the 6th, and that's in meters. So these are those two values that you would need then. And of course, G was listed before. So you would plug those numbers in, and you can then calculate what the force of gravity, would be at the surface of the Earth. And if you run those calculations, you'll end up with an answer of 9.8. Because that's what your force of gravity would be equal to. It would be based on the mass there. So yeah. You would actually calculate that G value, you'd find that this corresponds to, M times G, mass times 9.8. Now, what we have to be familiar with here is most of the time, objects are not orbiting the Earth from the Earth's surface. They're orbiting a certain altitude above the Earth's surface. So that's something that we have to make sure that we take into account here. So usually, instead of just putting the radius of the planet or the star there, you have to also take into account how high above the surface the object is doing the orbiting. And so you'd have that plus altitude y there, and that's what the y would stand for. That's your distance from the Earth's surface to where the object is. Questions so far? Okay. So let's just say we want to figure out a certain speed that an object needs to have if it's a certain distance above the Earth's surface. If we're looking for a particular speed like that, what we're looking for is something known as an orbital velocity. And so let's just talk briefly about an orbital velocity. If you're in orbit around something, you have to be going at a very particular speed. If you go any faster, your orbit will grow and grow and grow until you leave that system. If it is too small, then you will eventually just fall into whatever it is that you're orbiting around. So you do have to have one very particular speed. And even things like the International Space Station and space shuttles, when they're up there, they do have to correct every so often to make sure that they're at that very particular speed, so bad things don't happen. So let's think about this. If something is in orbit, the only force that's acting is the force of gravity. Because if you're in orbit, there's no other force pulling or pushing on you. Gravity's the only thing that's causing you to move in that circular motion. And what that means then is because you're moving in that circular motion, this gravity is equal to your overall centripetal force, your overall net circular force. So it's equal to MAC. It's the only force acting, and therefore it's equal to mass times acceleration here. Just like if something was moving in a straight line and it only had one force acting, that force would be equal to MA. So, if I want to figure out the orbital velocity of an object that's orbiting at a certain distance, here's what we got to do. Force of gravity we already redefined. And centripetal acceleration, like we've talked about, is equal to v squared over r. And this is kind of our setup then. We need to solve for velocity. If we solve for this v in this equation, that number will tell us the particular speed we need to have to be in orbit around an object that has a mass, whatever that value is. So let's just see what pops out of this equation. Little masses cancel out. That r goes away. That square goes away. And we're just left with v squared on the right side of this equation. So all this boils down to then, I'm going to call this v orb for orbital velocity. Simply equal to the square root of gm over the distance. So let's just say we've got the Earth here, and an object is orbiting, we'll say, 20,000 meters above the surface. And that's the spot that it's orbiting. If we wanted to plug the correct number in for the radius here, what we'd have to make sure that we remember to do is put in, first off, the radius of the Earth, and then add the 20,000 to it. Because remember, this r is the distance from the middle of the big mass to wherever the object is orbiting. So that radius of the Earth, 6.37 times 10 to the 6th meters, that plus 20,000 is what would go down here for that radius. And you could do this in another way too. Maybe instead of looking for that particular orbital velocity, maybe you wanted to solve for this. Maybe you know that you can throw something at 60 miles an hour, and you want to figure out how far above the Earth's surface you need to be for an object to actually go into orbit at that speed. You can figure that out too. Because if under here this r is equal to the radius of the Earth plus some altitude y, all you got to do if you want to solve for that particular altitude, and you know the velocity, you know these two numbers, and you know the radius of the Earth, of course, it's just a matter of isolating that altitude y. So you would we'll take you through this here. So v would square, so that we can get rid of the square root. So that's gm over radius of the Earth plus altitude y. And what I would do then is I would multiply both sides by this re plus y, and then divide both sides by the v squared. And finally then, to figure out that altitude, you would just subtract the Earth's radius from both sides. And that would then go away. So this is just rewriting that equation to solve for a particular altitude if you know what velocity you're looking for to be in orbit. If this was something you were trying to figure out in terms of, like, maybe you throw something 60 miles an hour. I calculated this once. It turns out you'd have to be all the way out pretty much where Jupiter is, and that's where 65 miles an hour would give you an orbit around the Earth. So you got to go an awfully long ways out there to make that speed be orbital. A couple other things just to mention. Again, in order to maintain this orbit, you do have to be traveling very quickly. The International Space Station is traveling at about 5 miles per second, so these speeds are just enormous. Questions on this? Okay, let me see if there's anything I missed. No, that about does it. I can show you a couple other cool things here that the folks at home, unfortunately, will not be able to see. So